Everyone. So in this video, we are going to learn how to delete a node in a threaded binary tree. So in the previous lectures already we understood what is threaded binary tree, what are the advantages, the disadvantages, and also how to perform the insertion operation. So in this video, we are discussing specifically that how to delete a node in a threaded binary tree. So let's start. Now, in threaded binary tree, we are going to delete a node in the same way. So let us recall that threaded binary tree is a binary search tree with some extra provision that we have added here, that the null fields are going to store the addresses of the previous node and the successor node. Now, the deletion that we are doing in the threaded binary tree is same like we were doing in the binary search trees. So quickly recall that in the binary search tree, we have three kind of possibilities when we delete a node. To delete a node, it may be a leaf node, that is called case one. And the case two is when you delete a node, then there is maybe one child of that node may exist, that is case two. And case three is there is a possibility that when you delete a node, that node which we are deleting has two childs. And we have already learned that how to handle all these cases. Now, I'm assuming that you're already aware that how to do the deletion in the binary search tree, and then we can only understand this. This is case one, the leaf node to be deleted. So here, if you look, we are deleting 14. So 14, you can see is 14 is a leaf node. So how we proceed? We start searching for 14th node. So we start from the root. All the operation that we perform on the tree starts from the root. So we start from the root. We compare is the key value matches with the node that we are looking for. No, 20. This is 20. We are looking for 14, which is less than 20. So we go to left, and then 14 is more than this. So we can come here. 14 is less than this. We come here. So finally, we identified that this node to be deleted. Now this is a node that we are deleting, and this is a leaf node. So when we delete a leaf node, so in the general case, if this is just a normal binary search tree, we delete it. But now in the threaded binary tree, we have to also maintain the addresses of the successor and predecessor node. So now have a look. If this node is deleted, then this is the impact of the deletion. Now we will look this kind of structure after deletion. So what is the difference that we see? The difference that we see is this is the space that is pointing to the child, but now this is pointing to 10. So here again, let me recall that when I say successor node and the predecessor node, I am talking in context of in order traversal. So earlier 14 is the previous node of 16, but if 16 is not existing, then the previous node of 16 must be 10. So how the 16 going to connect to 10? So actually this address need to be transferred here. So the node that we are deleting, if it is a child node, sorry, if it is a leaf node, then whatever is there at the left field, we are going to write it here. So you can see here that now 16 is going to connect, and the other tree will remain unaffected. It will have the same kind of structure as you can compare. The only thing that we see is this part is going to change. So if this is the left child of the parent, so this is the left child. So what is required? We are going to write parent left thread equals to true, because now this parent, this is the parent and this is a child that we have deleted. This is no more a child address. This is a kind of address of the predecessor node, which is a thread. So we need to also keep this boolean value for this node equals to true. That means that this address is representing a thread now. And parent left means parent left address is equals to the parent ptr left. Ptr left is a node uh, that we have to delete. So this address we are writing here, and then we have able to manage easily. Similarly, you can think about a situation when the child that we are deleting means the node that we are deleting means the right node we are going to delete, and this is also a leaf node. So we'll look to the situation. So have a look here. You can see now we are deleting 17, so we know how to proceed, and we find that this is a node to be deleted. This node is deleted just simply in a case of binary search tree, but because this is a threaded binary tree, or we call it TBT, is a threaded binary tree. So in the case of TBT, you can see after the operation, we are having this kind of structure, and just find out the difference that we see between the two figure. So here you can see that now this node is pointing to this node, and how this address has been, find out. This is actually find out from here. So in the actual tree, in the previous tree, the address of this node 20 is actually found out here. Now, before we delete, we will pick this address and keep it here. So what actually we did now, this node is going to point to the successor node. So that means this is basically presenting a thread. So we need to write the parent right thread field is going to be true. Earlier it was false because the child is there. Whenever in the node the child is existing, then the thread field is actually false. If the thread is existing, then we make it true. So this becomes true. And also this address, that is the PTR right. The PTR address we are going to assign to parent right. So now you can see it is done, and we are able to manage our tree. So only two statements are actually required. Apart from that, you can also write one more statement, ptr delete. That means after doing all these kind of settings while assigning the address correctly, this node is no more required. You need delete it. So when we write this delete statement, this basically says that just free the buffer which is we have used for this node. Now this memory space is available for other programs to use. So it's always good to delete the node that we are not interested. Okay. So this is case one. Now let's move to the case two. Okay, in case 2, the node which we are deleting has one child. So here we are going to use two procedure in successor. This is called in order successor. This is basically to find out the next node. And in order predecessor, we call it in pred. This is basically to find out the previous node. What does it mean? It means if we are going to do in order traversal. So if you look here in this traversal, so this is the in order traversal. So in order traversal is this. So if I say what is in suc of this node, so in suc of means the successor of this node is 20. This is the answer. And what is the predecessor of this node? That is 16. So we have two procedure. We will see that how the procedure is being uh, logically defined. So we'll see the logic of this procedure. But the purpose of the procedure of this procedure is to find out the next node and the previous node. Let us first understand that how these two procedures are working, because we are going to use this in successor and in predecessor in our logic. So let us first understand this. Okay, so now you understand how this in successor method work. So our intention here is to find out the next node of any given node. So now let us take the situation. Let's say this is what the node we are having. So actually in this case, uh, if we do the in order traversal, so we are at the E. The what comes before E is F, and what comes after E is A. Okay, so the successor node is A. So we are saying if PTR R thread, if the thread is true, that means the this node is does not having a child. So if the child is not existing, that means that the thread value is true. That means PTR right, whatever the address is there at the right link is the successor of this node. So in this case, it is A. But let's say there is a node existing. There's a right subtree existing. Let's this is a scenario. Okay, let's this is a scenario. In this case, this is going to become your successor of E. So what do we do? If this case is not true, we will be writing PTR equals to PTR right. That means we move to the right subtree. And then to find out the successor element in the right subtree, we know the logic that the smallest value in the right subtree is going to become a successor. So if the tree is like this, if the tree is like this, that means there is no left child. So we are here, and while PTR left thread equals to false, uh, left thread equals to false means there is a child existing, because if the thread becomes true, that means the child don't exist. So if the child is existing, we have to go up to the last label and look to the deepest leaf node, that is the successor. Now let us understand in a very simple way. Let's say this is not existing, then the successor of this node is this node, because there is no need to go through these statements, and we will simply get our answer. But let us assume that we have a scenario like this. We are looking for successor and we have this scenario. In this case, the successor will be this node. Means the node that comes after E is this one. So how do we reach here? So you can go to the right node and then you have to keep moving up to the last node. So we can now this loop is comes in place. If the pointer left thread equals to false, means left thread equals to false means this node is having a child. So we come here and again we check, does this node having a child? Yes, you come here. And does this node having a child? No, we stop and we will return the address of this node. That means this node is going to become the successor of this node. So this is how we can find out the in successor. So now we'll be using insect method to find the successor element. Similarly, in the same way, but in the reversely, we can understand that how to find the previous element of the given node. So you can see here, if pointer left thread equals to true, that means there is no child existing. Then you can directly, for example, here you can see here for F. In F, the left thread is true, means there is no left thread existing. Then you can look to the left address, and that is basically B. So the previous element of F is B. Similarly, we can find out that what is the previous element of any node. Now we need to know the logic. For example, if we are going to the left subtree, in the left subtree, the maximum value of the key is the previous node. So if this is the status, if this is the status, then this is the answer. If this is the status, if this is the kind of, you can say status, or you can say the structure of your tree, then this is going to be your answer. Okay, so in the left subtree, the the previous element is the maximum element, and in the right subtree, then the next element is the smallest element. This we know. So I believe you understood that how the insect is working and how the inpred is working. Now we are going to use this directly and see how the deletion can be performed. So let's move back to our case 2. So this is the case 2 that we were discussing. This is a scenario where the node to be deleted has only one child. So let's understand. Let's say we are deleting 30. So 30, this is the node to be deleted, and this node has only one child. That is the right child. So you can say we are deleting a node that has a right subtree or right child. Now, because we are going to delete a right, we are interested to find out the next successor element. You must be knowing that how to handle the case 2 in BSC deletion. So actually what we are going to do, we are going to remove this and we are going to connect this node to this node. Okay, means 38 is going to connect with the 50. So what is the impact if we do this operation? So this is very straightforward when we do BST, but in the case of TBT, means in this tree, we need to also take care of these pointers, that how to connect these pointers. So if you look at this, now 30 is going to delete, and now this 34 is going to connect to this 25. You see here. Now if you compare these two things, then we will find a difference here. This is the difference that is visible to us. And other things are almost the same, because this thing is only visible. So how do we get the address? So this address you can find out. Before we delete this, we can this node, we carefully write this address here. So what is going to happen? This is going to overwrite, and this is now going to connect to this. So you can see now, what is this node? This node is a successor of this node. So we are using S. So S is basically uh, find out by using in successor method. So we delete this node. Let me clean this area. So we need to delete this node. So we will find the successor node, because successor node is used to do some adjustment in the pointers. But otherwise, we have to connect this. So how do we are doing? We find the successor, and then we will write successor left equals to P. Now, what is the now what is P? P is a predecessor of this node. So in the successor left means in this node, the left we will write the predecessor, and that is basically representing to the this node. So we'll write here the address of this node, and we are done. Or you can, this is like more like accurate, more generalized form. But for this scenario, you can also realize that S of left equals to PTR. PTR is a node that is to be deleted. So we can say whatever is in the PTR left, that we are going to assign to this successor node left, and we are able to handle it. Apart from this, the one more thing that need to done, that is parent child link. Means this is the node that we are deleting, and this is the parent node. So the parent child link means, for this parent, the child link will be assigned the child link of the PTR. Now, when I say child link, this is a very generalized partial statement, because here I am not mentioning the right or left link, because this is to be applicable in either case. It is the right child, it will be suitable for right scenario. If it is a left child, suitable for left scenario. So child link is a generalized statement that is actually applicable for both. So the parent child link should be given the pointer, means the pointer means the node that we are deleting, this PTR child link. So this link we are going to connect here, and so how we are able to connect to this node. So I think this is okay. So these are the statements that is to be used. One is successor left equals to the predecessor, and the parent child link equals to the PTR child link. Now, the other thing that we can discuss or understand in the reverse scenario is the node that we are deleting has our left child. Now, this is case 2. It has one child, and the child is a right child. Now, we can look to the case when the node to deleted has a child and the child is a left child. So, almost the same thing we are doing, but in the reverse way. What does it mean? Let us have a look. So let's have a look that now we are deleting a node that has a left subtree. That means we are deleting 16, and you can see that 16 is a node and this has one child, which is a left child. So if you delete this node, then you can find that this node is basically pointing to this, but after deletion, this node. Now, what is this node? This is basically a previous node of this. So if it is going to become a left child, then we need to find the P, the predecessor of this node. We can find with this. So we can write the P of right. I mean, this is the P node. So when we apply this method in pred on this node, we are able to get this node. And what we're going to write? We write P right, means P is this node right field is equals to the S. S means the successor of this node. So that means successor of this node is this one. That means this 15 is pointing to this. You can see here. So this is the only thing that is visible when we are in the case 2. Or this is a generalized way of writing the statement, but this is a very specific to the scenario. You can say the P right means this node right is equals to the PTR right. And also, once we delete this node, this is going to connect to this node. So you can say the parent child link means I am talking this as a node to delete it. So this is the parent node. So the parent link is going to connect to the child of this node. So you can see here. And we are done with the deletion. And also we have carefully set the address link for the thread as well as child. Okay, so this is done. Next, have a look to the third case. Now in case 3, the node to be deleted has two child. So you can see here, this is case 3, and we know in the case 3 in the BST, we have a choice of either moving to the left subtree or right subtree to do the deletion. So what we see in case 3 here is whenever the case 3 appears, means a node that is to be deleted has two child, then this has to be handled by either case 1 or case 2. So we'll see that every case 3 in the TBT is going to handled as a case 1 or case 2. So if you look at this, here we are going to delete 10. So 10 is this node. It has both the child left and right. So we need to look these cases in context of case 1 and case 2. And already we have discussed that in either of the case 1 and case 2, what are the statements required. So let us take some example to understand it. So before we move to an example, just have a quick kind of summary that what we have seen so far. So case 1 is leave node to be deleted. Then these two statements are to be written if the right child node is the right child of the parent, and if you are going to delete any node which is basically a left child of the parent, then we are going to do this thing. And if the node deleted has one child, and one child also has two scenarios, this child may be a right child or a left child. This is the case when it is a right child, we are doing this operation, and when it is a left child, then we are doing this operation. So now in the case 3, we are going to use all these means these basically statements to handle case 3. So let's take some example. So now look at this example. So this example, let's say we are going to delete 10. So delete 10, that means we are here 10 to deleted, and 10 has two childs. Okay. So let us understand how we are going to handle it. I'm assuming you are actually recalled at how the deletion is done in the BST when it has two child. So I am using a successor approach where I am going to go to the right subtree. Okay. So what is required? I will find the successor node of this, and successor node of this I can find out with this, and I'm able to find that this is going to be a successor. Okay. Successor means what comes after this node. So if you look at the sequence, so the sequence should be, actually the sequence is not correct. It should be 5, 10, 13, 14, 15, 16. So means actually this is correct, but the only thing which is missing here is the 13 is missing here. So 13 should actually come here. It should come here. This is the sequence. Okay. So the successor of 10 is 13. Mean this is the successor. Okay. So what we are going to do? We are going to replace this value with here. So we are going to write 13 here, and then we move to the right subtree and delete the 13. So what exactly we get? So we get something like this: 20, 13. This is 30. And here we have the node which we have deleted. So in the binary search tree, this the next node to be replaced. So in the right subtree, we find the minimum node. We are going to replace this node here, and then we search in the right subtree this particular node to be deleted. So if you look to the scenario, this scenario is basically converted to case 1 when we are deleting a when we are deleting the the leaf node. And more specifically, this is a leaf node which is basically a left child. So if you look to this case 1, case 1 is this: a node is the right child of the parent, node is the left child of the parent. So actually this is to be required. Now let us see that how to manage this. So before that, we will also see the status of the pointers, that how the pointers are to be taken care. So this is the first node. It will actually go to the header node, this address. This goes to the header, and this will go to this node. This will go to this is sorry, this is 15. Okay, so let me correct this. This is something, the mistake that we did. It is something like this: 15. Okay, so let us quickly set the addresses. So the previous of 15 is this. So we'll make this pointer because this is going to be a leaf node. It has the two threads. It is this, and it points to this. This points to this, and it has a left side. Okay, I think we are done. Okay, and also 14 is going to now point the previous node. So this points to this. So what we have seen here? We have seen that in if you look to this two, this is a old tree. Before old tree means before deletion. This comes before, after deletion. So what difference we will see here? So it is actually almost the same structure. The only thing that we see is now this is no more existing, and also for this node, this is pointing to this upper node. Okay, and this is no more existing. It means there's no more child. So actually, what we are doing, this is going to become thread. So one thing is this is a kind of parent, and this is the node that deleting. So we will say parent left thread is going to be uh, true. This is one thing, and also we are going to connect this node with this node. So we are going to write this address here. So we'll write here mm, parent left is equals to ptr left. So you can see we are in this scenario, and we have set parent thread equals to true and parent left equals to ptr left. That means though it is actually a case 3, but we have handled with case 1. Okay, so I believe this is understood to you that how we are going to handle the case 3 by converting or realizing as a case 1 or case 2. So let's take another example to understand in a better way. Let's say delete 20. Let us understand with one more example. Let us say I want to delete 20. And in the case of BST, it is case 3 where we have two child for node 20, and we need to decide what to use. Let's say I decided to go with the left subtree method, with the predecessor method. So I'm going to look to the left subtree to proceed. And if I go to left subtree, I will find the maximum value here. So I will be going to use this method, and this method is going to give us this node 16. Okay, so I believe this is okay to you. So how the things are going to happen? This 20 is going to replace with 16, and this node is to be deleted actually. So what is the structure that we find after the deletion? We will find something like this: 16, and then we have 30 here, we have 10 here, and then with the 10, this is 16 here again, which is to be deleted node, and then we have 14, we have 13, we have 15, and here we have 5. Okay, so actually this is case 3 in our BST, but when we look to it that how it is handled, this is to be treated as case 2. Now case 2 why? Because actually we are going to delete this node, and this node has one child. So already we have discussed in the case 2, the node to delete has one child, and more specifically, the child is a left subtree. So we'll have a look here. Already we have seen case 2. In the case 2, we are getting a node with the left subtree. So actually we need these two statements to represent our tree. So what exactly is the impact that we see after deletion? So actually what is going to happen? The tree is going to look like this: 16, 10, 5, and this is going to remove. So we have already mentioned that the parent link will be given this pointer link. This is the node that we are reading, we call it ptr. So whatever the ptr child, that child we assign to parent. So you can see here, we have noted here, the ptr child is assigned to the parent. So we have this thing, we will have 14 here and 13 here and 15 here. And what other things that we have seen? So let us look to the status of the addresses that we are assigning. So this 5 will be going to connect to the header node. This is the connect to the header node, and the left is connecting to this node 16. This is also connecting to this node, and this connects, the left connects to this. It's a thread connect to this. It is also leaf node, so the right connects to this, and the left connect to this, and so on. So now let us compare to this structure. So assume this is a kind of node like this. You can assume like this structure. So what difference is visible here? So here you can see in this two trees, this is actually now gone. So if we look into this figure, the other difference that is visible to us is that earlier 15 is pointing to this node 16, which is no more existing here. And so now 15 is actually pointing to the node which earlier this node is pointing to. This node is pointing to this node, okay, at the root node, you can say. Just don't look at the value. This is pointing to root node. Now This node is pointing to the root node after the deletion. So what we have required that this address to be written here before we delete. So the so what the statements we are going to write. So you can see here, this already we have seen that the parent child is will be the pointer child that we have seen, that is not deleted, and this is going to be connected by this. Other thing is, because this is a left child of the node that we're deleting, so we are going to read this statement and it says p right. So we need to find out the predecessor of the 16. So predecessor of this node 16 is 15. So this is p, means p is basically representing the node number 15 here. So p right means the link of this field, this right link of this field 15 is equals to the ptr right. This is uh, what we can write here. P right is equals to PTR right. Otherwise, the more generalized way of writing the statement is you can say P right means the predecessor right is equals to the successor, that is S. And successor of what? Successor of the node which we are going to delete. So I think this is okay. And you realize that again, the case 3 is being handled as a case 2. This is case 2 basically, right? A child having, sorry, a node having one child. Okay, so let us take one more simple example, the last example, to understand how the deletion to be handled. So we have seen how to delete 20, we have seen how to delete 10. Let us take delete 14, because delete 14 is also a case 3 scenario which has two child. Okay, so again, this is going to be simple. To delete 14, we will start from the root and we come to this node and we realize that we have two childs are here. So we will have to decide which way we are following, either to the left subtree or right subtree. Let's say I decided to go with the left subtree. So I find, so if I go to left subtree, I will find the previous element of this, and that is basically I can find out with the help of predecessor method. Okay, so the previous element of this is actually find out by this, and actually there is nothing, so this is the only thing that you can find out. This is 13 is there actually. So we find this node 13, that means 13 to be replaced here, and then you are going to pass left subtree and search for 13 delete, so this node to delete it. Now this is just a case 1. Case 1 means we are going to delete a node which is a leaf. So here you can see this is case 1, and case 1 has again two scenario, that the node which is a leaf is a left child or a right child. So in our case, this is a left child. So we can look to this part. So what is required? So actually, if you draw the tree and you can see the difference, so 20, 10, 30, and 16, 14, and because 14 is deleted, this has actually become 13, and this is the node that we are going to delete. So after deletion, what is the impact? Actually, you will going to connect this with here. This will connect with here. This you connect with here. This with here. So actually, the other part of the tree remain the same. The only thing that is visible to us is earlier this there is no connection. Mean this node is having no connection to this, and this node is no more existing. So what we are doing, we are actually shifting this address to this node, so this node can connect to this. So you can write it here like this, that as it's shown here. The very first thing is this is no more having a child. This was earlier having a child, so this field was true. Sorry, false, because there is no thread. But now the child is not existing, so we will set that parent left thread equals to true, because now it's having a thread. And the second statement is parent left equals to the PTR left, means this left is the value which is taken from the PTR left. So again, we are started with case 3, and later we have find that case 3 is now changed to case 1. So in the case of TBT, threaded binary trees, whenever we are doing deletion, we have to handle two cases, case 1 and case 2. And in case 3 is there, we need to look to it, and then we find that case 3 to be converted to case 1 and case 2. And this is all. I hope you understood the deletion operations in the threaded binary tree. So, in order to have a better understanding, I do advise you to do some more practice. And that's all for this lecture. Thank you very much.